Dear students, welcome to 10th online class of Control System Engineering. In previous classes, we have discussed how to develop mathematical model for different physical systems, also expressing their differential equation in terms of transfer function using Laplace transform and expressing their differential equation in terms of state space model. And the systems mostly studied were electrical networks, translational mechanical, rotational mechanical, and electromechanical. Dear students, now we will study time response of any physical system, which is CLO3 of this course. Dear students, in this chapter of time response, you will study how to find time response of a system from poles and zeros of the transfer function. You will study about transient response of first order system and will write general response of second order system given the pole location. You will find the damping ratio and natural frequency of second order system. Also the transient specifications, which include settling time, peak time, percent overshoot, and rise time for underdamped second order system. Dear students, now coming to contents of this lecture. In this lecture we will study poles, zeros, and their effect on system response. Then we will start first order systems, in which we study about their transfer functions, time constants, rise time, and settling time. Dear students, output response of a system is the sum of two responses. One is forced response and second is natural response. Now, natural response is due to transfer function or due to the poles of the system, where forced response is due to input of the system. Now, if we have output response relation in frequency domain, then we can find time domain response with the help of inverse Laplace transform. But this conversion from Laplace domain to time domain is time consuming. So we are looking for a method through which we can find result in minimum span of time. For this, we will use poles, zeros, and the relationship to the time response of the system. Dear students, now we will study poles and zeros of a transfer function. Starting with poles, the values of the Laplace transform variable s that cause the transfer function to become infinite, or any root of denominator of transfer function that are common to roots of the numerator are known as poles. In the similar way, the values of Laplace transform variable s that cause the transfer function to become 0 or any root of the numerator of transfer function that are common to the roots of denominator are known as zeros of transfer function. Dear students, now with the help of example, we will study system response with the help of poles and zeros. In the given figure A, we have a system whose transfer function is s plus 2 divided by s plus 5, and input applied to the system is step, which means that R of s is equal to 1 over s. Figure B shows pole 0 plot of the system. In this we have a pole at -5 and a 0 at -2. Now we want to find output or system response which is equal to transfer function of the system multiplied by input, which means g of s into r of s, and this will be equal to s plus 2 divided by s into s plus 5. Now for the response of the system in time domain, we will use partial fractions, and this will be equal to a divided by s plus b divided by s plus 5. Now solving for the values of a and b, c of s will be equal to 2 divided by 5 whole divided by s and 3 divided by 5 whole divided by s plus 5. Now using the rules of Laplace transform table, we will get our desired system response in time domain, which is c of t will be equal to 2 over 5 plus 3 over 5 multiplied by e power minus 5t. Dear students, same example can also be studied with the help of pole zero plot. Figure A represents the original system with transfer function s plus 2 divided by s plus 5. Input of this system is step, which is equal to 1 over s. Figure B shows pole zero plot of transfer function of the system. In this plot, we have a pole at minus 5 and a 0 at minus 2. Now if you look at figure C, in this we have 3 pole zero plot. First plot represent pole of input which is at origin. Second plot represent 0 of the system which is at minus 2. And the last plot represent pole of the system which is at minus 5. If you look at output transform equation, this equation is sum of two terms. One is having a denominator equal s, which represent input pole. Second term represent denominator s plus 5, which represent system pole, and numerators of both the terms are defined by zeros and poles of the system. Now if we look at time domain response, c of t equals 2 over 5 plus 3 over 5 e power minus 5t. If you take inverse Laplace of 2 over 5 divided by s, we get 2 over 5, and this part was due to the input pole, so this will be our forced response of the system. In second term, we were having 3 over 5 whole multiplied by 1 over s plus 5. Now if we take inverse Laplace of 1 over s plus 5, we get e power minus 5t. So this portion e power minus 5t due to system response or pole of the system, and this will be our natural response of the system. Dear students, now we will summarize last slide here. The first point is the pole of the input function generates the forced response of the system. In this, a pole at origin generated a step function at the output. Secondly, the pole of the transfer function generates natural response of the system. In this, the pole at minus 5 generated e power minus 5t. Third one is, if we have a pole minus alpha on the real axis of S plane, this will generate an exponential response of the form e power minus alpha t. And as you move pole to the negative side of the real axis, the response of the system will become faster and exponential transient's response will decay to 0. Last one is the zeros and poles generates the amplitude for both forced response and natural responses, which we have find out in partial fractions calculation in A and B. Students, in the given example, we have a system. For this, we have to find out output equation C of t in terms of forced response and natural response. If you look at the figure, which defines a system with 3 poles, one is at -2, other is at -4, and the last one is at -5, and a 0 at -3. Input of the system is step. Now we know that poles of the system generates exponential part as a part of natural response, and the pole of input generates forced response. So the given output transform equation will consist of 4 terms. First term will be due to input pole, and this will be our forced response. Second, third and fourth terms of the partial fraction will be due to poles of the system, representing pole at -2, pole at -4 and a pole at -5. These 3 terms combinedly will form natural response of the system. Now taking inverse Laplace, we will have C of t equals k1 plus k2 multiplied by exponential power -2t plus k3 multiplied by exponential power -4t plus k4 multiplied by exponential power -5t. Here k1 will be our forced response, where terms with coefficient k2, k3 and k4 will be our natural response corresponding to the pole at -2, -4 and -5 respectively. Dear students, now we will start first order systems. In this topic, we will discuss time response of first order systems and transient characteristics associated with the response of first order system. Students, transfer functions of the system with a single pole are known as first order systems. In this topic, we will study transfer functions of first order system without zeros. If you look at the figure A, the system in figure A is represented by transfer function g of s, which is equal to a divided by s plus a. Means the system is having a single pole. Input of system is r of s, where c of s is output of the system. Figure B represent pole 0 plot of the first order system. Now if we assume that step input is applied to the first order system g of s, then output of the system C of s will be equal to r of s multiplied by g of s, where r of s is equal to 1 over s and g of s is equal to a divided by s plus a. Now using partial fraction, we will find output transform equation, and then we will take inverse Laplace transform to get C of t, where C of t equals 1 minus e power minus at, or sum of forced response plus natural response. Here natural response is equal to minus e power minus at, or the response due to the pole of the system. where forced response is equals to 1, which is. Dear students, as discussed in the start of this chapter, mathematically, total response of the system is equal to forced response plus natural response of the system, where on graph, total response of the system is divided in two parts. First part is known as transient state and the second part is steady state. Students, whenever our system is at rest and the moment we apply the input to the system, due to this sudden changes in the response of the system occurs. This is known as transient state. And whenever these transients get settled down and the system starts working normally, is known as steady state of the system. Students, now we will discuss significance of parameter A from transfer function of first order system. For the first order system given in the figure A, step input is applied and output in time response is equal to 1 minus e power minus at. Now to find significance of parameter A, we will find system response at time equals 1 over a seconds. If you substitute time equal 1 over a seconds in exponential term, we get 0.37. Now substituting value of natural response in total response equation, we get output of the system at time equals 1 over a second equals 0.63. Now if you look at output equation for this system, which is C of t equals 1 minus e power minus at time t equal to 0 seconds, system response is equal to 0. And now if you analyze response of the system at times t equal infinity, the total output of the system will be equal to 1, which implies that final output of the system is 1. Dear students, from the previous slide we studied that at start or at time equals to 0 seconds, response of the system is equal to 0, where at time equals to infinity, the response of the system or output of the system equals 1, which means that final value of the response is 1. Now we will define time constant. Time constant is the time it takes for the step response to reach 63% of its final value. We call 1 over a the time constant of the response. And the time constant of the system can also be defined from the output equation. The time required for the exponential term e power minus at to decay to 37% of its initial value, which is 0.37. Now time constant is represented by tau, which is equal to 1 over a seconds. Now if you look at the figure, which represents step response of first order systems, where time axis is divided into time constants against output of the system. After the time of one time constant or 1 tau, output is equal to 63% of the final value. After time equals 2 time constants, output of the system reaches 86% of the final value. After the time of 3 time constant, output of the system reaches 95% of the final value, and After 4 time constant of time, output reaches 98% of the final value. In this figure, delta represents final value of the system. Dear students, now we will study transient specifications of first order system. In these specifications, we have rise time and settling time. Now we will study rise time. Rise time, rise time is defined as the time required by the first order system in which its output move from 10% of the final value to 90% of the final value. Now, for rise time, we will solve output equation of the system for value of 0.9 and 0.1. We will find the desired time and find the difference among two. If you see the figure which represents step response of the first order system, in this initial slope is equal to 1 over time constant, which is equal to a, and time axis is again divided on the basis of time constant. Now for rise time, we will find the difference of time for system output 0.9 and system output 0.1. Or mathematically, rise time will be equal to 2.31 divided by a minus 0.11 divided by a, and from this rise time is equal to 2.2 divided by a for a first order system. Dear students, second transient specification of first order system is settling time. Settling time is defined as the time of the system in which response of the system reaches and stays within 2% of the final value. For instance, final value is equal to 1, so the moment system response reaches 0.98 and stays within the limit, this will be known as settling time. For settling time, we will substitute output of the system, which is C of t equals 0.98 in output equation of the system. So we get settling time equals 4 divided by A, or this is also equals to 4 ta, studied in previous slides. Or in simple word, settling time is the time the moment transients are settled down and system response is in equilibrium state or no changes occur. Settling time can also be verified from the step response given in the figure. The moment output of the system reaches 0.98 and after this system response stays within the limit, the first time system reaches 0.98, the time corresponding to this is known as settling time. Dear students, now in the given example, we have a first order system for which we have to find time constant, settling time and rise time. Students, now in the solution, if we compare given transfer function with the one in figure A, which is A divided by S plus A, we know that A equals 50. Now time constant is equal to 1 over A or 1 over 50 and its value will be 0.02 seconds. Settling time is equal to 4 over A or 4 over 50. So settling time will be equal to 0.08 seconds. And finally, rise time is equal to 2.2 divided by A or 2.2 divided by 50. Here rise time will be equal to 0.044 seconds. Now if any of you have any questions, please ask.